Here we are with a lecture on section 1.7 about limits and continuity. And first we're going to do this in sort of the pre-calculus way you look at limits and continuity, which is not a very mathematically formal definition, but it does the trick just for understanding things and knowing how the graphs should look and everything. So here's a rough definition of a continuous function. So we say a function f of x is continuous on an interval from a to b if you can draw that part of the graph without lifting your pen. Let's remember that the interval from a to b is another way of writing the set of x values such that x is greater or equal to a and less than or equal to b. Just a quick reminder of that. So this is a set of x values that includes a and it includes b and also everything in between. So if you can draw that part of the graph without lifting your pen, it's continuous. So for example, here is the graph of a cubic function. This is an example of a polynomial, like in section 1.6, and you might know that they are always continuous. That means then it's continuous on any interval you want. So let's say I use the interval -1 to 1, which you can see is graphed here. I'm going to plug in -1 and get something like -5, and then you can draw the whole part of the graph until you get to x equals 1, and there it's +5, and I didn't have to lift my pen because there's no gaps in it, there's no breaks, so it's continuous. Now this function is also continuous actually on any interval, so it's continuous on -infinity to infinity, meaning you can draw the entire graph if you could start at -infinity, which you can't really do, which is why this is a rough definition. But anyways, if you could draw the entire graph because you had an infinitely big piece of paper, you would be able to do it without lifting your pen. All right, so this one here, f of x equals 1 over x, we know it has this asymptote here and an asymptote down here, and it is continuous on some intervals. So like if you want to plug in like x equals 1 to 2, let's say, then that part of it is continuous. You can draw that part of the graph. You could also say it's continuous on the interval, here's a big interval it's continuous on, -infinity all the way up to 0, but not including 0. Now remember, this is another way of saying the set of x values that are greater than -infinity and less than 0. So that interval on the x-axis here is like from there, like not actually including 0, but including -0.1 and everything, all the way out to -infinity out here. So that part of the graph, again, you can't really draw the whole thing, but you can still do it without lifting your pen. Okay, so, whoops. Okay, that worked. Okay, but it's this one here, 1 over x is not continuous on an interval containing 0. On, like, let's say -1 to 1, because if you were going to draw that part of the graph, you have to lift your pen to get from, oh, whoops, I guess I didn't learn my lesson about erasing that picture by accident. Let's try that a different way. Okay, so if you show the interval from -1 to 1 looks like this, it's all of these numbers in between there, and you could draw this part of the graph, and you could go down forever, but then you have to lift up your pen to come back up here. Okay, so that one is not continuous there. Here's another one. This is sort of a real life example where the cost of renting a car is rented, they charge by the hour. It costs $7 per hour, but they always round up. So for example, if you use the car for 55 minutes, then the cost of renting the car is $7. But then if you rent it for just an hour and 10 minutes or something here, then they round up to 2 hours and you pay $14. So this part of the graph you can't draw without lifting your pen, so it's not continuous there. But it is continuous on these smaller intervals, so I could say it's continuous on the interval 1 up to 2, including 2, but not on the interval, let's say, 1.5 up to 2.5. So yeah, you can draw parts of the graph without lifting your pen, but not the whole thing. So you can say, another way of saying this is that it's discontinuous at these points where you have to lift up your pen. Oh my gosh. All right, third time's a charm. Yeah, you could say it's discontinuous at the points where you have to lift up your pen. All right, so now let's have a rough definition of a limit, which is a super important concept in calculus, as you may know. So I'm going to pause this and then fast forward after I write it. All right, so a rough idea of a limit is that we say the limit as x approaches c of f of x is L if the values, the output values, or the y coordinates get closer to L as x gets closer to c. So this expression here, the limit as x approaches c of f of x, we think of that as the thing that that f of x gets closer to. Like what is the output of the function approaching? So another way to write this is we say as x values get closer to c, whatever that number is, the corresponding output values of the function get closer to this thing we call the limit. All right, so let's do an example of this. We have this function here. It's a rational function, so it might have some asymptotes, maybe not. Let's find the limit of this function as x approaches 1 using a few different methods. So first of all, using a table. So here's a table with some values of x plugged in. These are values of x that are less than 1, but they are getting closer to 1. So if you plug in 0, you're going to get 3 plus 0 times -1 over -1 works out to 3, then because the negative ones cancel out. If you plug in x equals 0.5, f of 0.5 will be 3.5 times -0.5 over -0.5, and the the x minus 1 parts cancel out there because it's negative 0.5 over negative 0.5. Same thing with 0.99. Only the 3 plus 0.99 does anything. What happens if you actually plug in 1? Plugging in 1 gives you here f of 1 is 3 plus 1 times 1 minus 1 divided by 1 minus 1, which this works out to be 4 times 0 divided by 0. So 0 divided by 0 is undefined. So this is the point does not exist when x equals 1, but that's okay with the limit. It actually doesn't matter. And then if you plug in some numbers a little bit greater than like so, then you can see you get things that are also pretty close to 4. So it looks from the table that as x approaches 1, we have f of x approaching 4. It looks like the values of f of x are getting closer to 4. So you'd say the limit as x approaches 1 of f of x is equal to 4 from the table. All right, how about using algebra? Let's do that in green. Using algebra means like just using rules about how to manipulate the symbols here. What do you know about this function? And simplify it if you can. That's what we're going to try to do. So what I'm going to do is look at this and say 3 plus x times x minus 1 over x minus 1. Two things could happen. This could be equal to one of two things. One, if x is not equal to 1, then that means x minus 1 is not 0. And then you can do a number divided by itself will always cancel out as long as it's not 0. But of course 0 over 0 is undefined. So this is actually just equal to 3 plus x, but only if x is not equal to 1. But if x is 1, then this becomes 0 over 0, and it's undefined. It doesn't exist. Now, we really don't care with a limit what happens at the actual value when x equals c. Like f of c doesn't matter with limits. We're just talking about getting closer to it, but not actually touching. So with that in mind, the only part of this function that we care about is the 3 plus x part, and 3 plus x, you can see, is just going to get closer to 4 as x approaches 1. So that's why you get the same result as we got before. So just verifying that result by doing it with algebra. Now let's look at a graph of the function. So let's head on over to a web browser with Desmos in it right here. So here is a graph of it. I just typed it in here, and it graphed me this line. And actually, you'll notice that this is a graph of just y equals 3 plus x. The function really is undefined at this point, but this is a limit of graphing calculators. You should be able to like zoom in and be able to tell somehow that it's undefined there. But graphing calculators usually don't know calculus, so no matter how much you zoom into this point, it just looks like a line that is continuous through there. But we know that's really not the way it's supposed to be. So it's a limit of it, but what I'm trying to say is you can still tell what the limit is, because as you plug in values of x that are closer and closer to 1 here, I'm going to copy this over. Okay, here we are again, back in the notes. So yeah, what we care about is that when you plug in numbers like 0.9, when you plug in numbers like 0.9 here, or 1.1, then what happens to the y coordinates here? So at points like this, we're getting outputs that are close to 4. And the closer that we get to x equals 1, without actually plugging in x equals 1, you can see that the y coordinates here, this drawing isn't very good, you can see the y coordinates are getting closer to 4. Anyway, so that's just trying to verify that from a graphical point of view. So it looks like we can see how all three of these methods are actually going to be important. Being able to see things when they're on a graph, understanding how that's related to the equation and doing it with algebra, and how you can see how that's related to a table of values. All right, so let's look at another kind of weird function here, sine of x over x. Now, again, you notice that if you take this function and you plug in 0 into it, and you try to do sine of 0 divided by 0, sine of 0 is actually equal to 0, and 0 divided by 0 is undefined. So what do? Well, we have to, you could either make a table. Instead of making a table, I'm going to look at a graph again. And for this, a quick reminder, we're going to use radians all the time in calculus. They work a lot better than degrees for a bunch of calculus things, and we'll explain why when we get into chapter 3, I think. But anyways, here's a graph of sine of x over x, and it looks like Desmos is using radians too, because it has a 0 at about 3.14, like it's supposed to. But what happens close to x equals 0 here? Well, I can see that if you plug in points like 0.1, where to go, 0.1 something, you get a result that's 0.99 something, pretty close to 1. And the closer that you get to 0, doesn't actually plug in 0, 0. Oh, 0 undefined, there. You can see that it is undefined right there. So Desmos seems to know about that. Excellent. So, but then if you plug in other numbers over here, you get things that are really close to 1. In fact, it looks like it's actually rounding up to 1 because it's so close. So from the graph, it looks like the limit is 1. So I'm just going to say that. Okay, sounds good. Now, the definition we had before had some flaws in it. For example, we said, like, what is the thing that f of x is getting closer to? That's a little vague, because it's getting closer to more than one number at the same time. So, for example, if I drive from Los Angeles to New York, as I'm getting closer to New York, I'm also getting closer to Iceland. I'm also getting closer to England, way across the ocean, but that's not really what we mean. And in math, you need to have definitions that everybody agrees on without arguing about, like, oh ho ho, you're getting closer to Iceland as you're going to New York. So that's the limit of your driving, but that's not what we mean. So we need a more formal definition. And for example, with let me go back a second. I think I forgot to say something with this one. You could also say that sine of x over x, it was getting bigger there. Like as x approaches 1, like it's going up here. So as you like walk to the top of this hill, you're also getting closer to x equals 2, even if you're not actually getting that close. So you could say that sine of x approaches 2 as x approaches 0, but you don't want that to be the limit. So how do we avoid that? So here's a more formal definition of a limit, which we're going to use. So we say a function f is defined on an interval around c, except at the point x equals c. So we define the limit of the function as x approaches c, written the limit as x approaches c of f of x to be the number L if it exists. Sometimes it doesn't exist. We'll get to that. And L has to satisfy these criteria. F of x is as close as we want to L whenever x is sufficiently close to c, but not at x equals c. And if this is true, if L exists, we write that the limit is equal to L. So this definition is kind of weird. It confuses most calculus students the first few times they see it. So this is the condition that has to be true here. That no matter how close we want f of x to be to L, like if we want to be within 0.5 units of L or within 0.1 units or 0.001 units, no matter how close we want to be, we can make sure that happens when for all values of x that are sufficiently close to c. Okay, pause it there for just a second, because my son woke up from his nap, but he's just hanging out in the other room now. He thinks I'm talking to him. Anyways, I have this little thing here which helps understand this more formal definition of a limit. And so when we say f of x is as close as we want, this is some... Okay, I'm going to pause it again. Okay, so as close as we want to L, we're going to use the Greek letter epsilon here to denote that. So in this case, if you make epsilon a little bit bigger, that means you don't want it to be that close, like within, I don't know, 1.1 units or whatever. Then is it possible to say that whenever x is within this little x interval here... Okay, let's look at what this definition of a limit means graphically here. So when we say f of x is as close as we want, I'm going to say that as close as we want is what we're going to call epsilon here. So meaning that within epsilon units of L is where f of x is supposed to be. Whenever x is sufficiently close to c. So that's what we're going to call actually within delta units. So that if we make delta small enough, how close x is to c, then that's going to guarantee that f of x is within epsilon units of L. So looking at the thing here, here epsilon is about 1.1, and yeah, if we make delta be like 0.01, that guarantees that for all of these values of x within this little interval here, you can see the corresponding f of x values that you get out are all within epsilon. And if you make epsilon smaller, then it gets harder. See, but if epsilon is like this, like 0.1, then this delta interval here is a little bit too big. It's not guaranteeing that f of x is within that small interval. So here we can make it just small enough, like 0.02. So yeah, if we get really close here with the x values, that guarantees that all of those f of x values are within epsilon units there. So because that works, that means that the limit of this function f of x does indeed approach L. And we're going to look at some examples of when this doesn't work. When you have a function that's not continuous, for example, it's not possible to find this little delta interval that makes everything work. Okay, so let's look at a more formal definition of continuity now. We say that a function f is continuous at x equals c if f is defined there, meaning f of x exists. That's the way you can read this. F of x exists, it's not undefined, and if the limit as x approaches c of f of x is equal to f of c. So both of those things have to be true. So in other words, f of x is the thing sorry, I said that wrong. F of c is the thing that f of x gets closer to as x approaches c. And if that's true at every point in that interval from a to b, then it means it's continuous on the interval. All right, so I just changed my mind about which example I'm going to do, so deleted a couple things. So let's think about what makes something discontinuous. Why would either the limit as x approaches f of x be not equal to c, or maybe if f of c is undefined but the limit exists? So there's a few different ways that might not work. So one way it might not work is if you have a weird function that is almost continuous, then it has a little hole, but maybe we're talking about at c equals 3. But then if you actually plug in 3, the result is something different. So maybe this point, the y-coordinate is 4, and here the y-coordinate is 2. So in this case, f of 3 exists, it is defined, and it is 2, but the limit as x approaches 3 of f of x is equal to 4, because the y-coordinates here are getting closer to 4. So those aren't equal, so it's discontinuous. And that makes sense because you can't really draw this other spot without lifting up your pen. So that's one way that could happen, or if it's just undefined. So for example, if you have something that just has a hole and doesn't have another point here, if this is at 2, for example, and this is a graph of y equals g of x, then and just g of 2 is just undefined, then it's not continuous because you can't draw straight through it. So that's this definition. Let's actually take a break here. I'm going to upload this video to YouTube and then finish it in a part 2 video.